Have you ever wondered how modern electric cars take these sharp turns with such ease? In this video we're going to discover all about it because we're building one with Lego Spike Prime. In the world of cars, making smooth turns isn't as easy as it seems, especially if you're having more than one wheel at the back, which most cars have. Today we will investigate how to program these motors so you will be able to make very smooth turns and very tight turns with this car. When a car turns, each wheel travels along its own circle. If both wheels would run the same speed, the car would want to go straight instead of turn. So we have to make the inside wheel turn slower so it runs a smaller circle than the outside wheel. In a previous video we showed that you could solve this problem with a differential gear. That's this kind of gear down here, and this Mindstorms version of the hot rod has a single propulsion motor, and using the differential gear it can transfer the power to the wheels, but at different speeds. In the Spike Prime version we don't have that gear in the set, so we need to use two motors and we need to calculate the speed differences in order to make smooth turns. Fear not, with a little math we can calculate exactly how fast each wheel has to turn in order to make smooth turns. And guess what? If we solve this math puzzle right, programming Spike Prime will be very easy. Now, let's solve the puzzle for calculating the wheel speeds. What do we know? There is a car here taking a left turn at a certain velocity v. We know that the left wheel has to run slower than the right wheel here, seen in green. But how much slower? Let's see if we can calculate that from some basic circle mathematics here. We know that both wheels and the center of the car drive the same part of a circle, and we could call that part omega. So it's the angle omega. If we express omega in radians, the distance traveled by each wheel is simply calculated by d is r, so the radius at which the wheel is, times omega. However, if we express omega in degrees, we have to calculate which part of a full circle omega is, and then multiply that by 2p to get the same results. However, let's use radians here for the sake of the exercise, and we know that since it's the same car and it's a solid construction, that all the angles are the same. So the angle traveled by the left wheel is the same as the angle traveled by the right wheel, as the same as the center of the car. Now, if we know that, these distances traveled are proportional to their radiuses. So you can express it also like this if you combine the two formulas up there. Since we are traveling at a constant speed, it also means that the speeds have to be proportional to the radii, because otherwise in a certain amount of time where the car turns for the angle omega here, the car would spin anywhere. So we have to assume that also the speeds are, or we don't have to assume, we just know that the speeds must be proportional to the radii here. So if we know that the distances traveled are proportional to the radius, and thus therefore the speeds are proportional to the radius, we can calculate the speeds from the central radius by looking at the difference here between the radius to the center of the car and the radius of the left and the right wheels, and the offsets, or the difference here, will be half h, or half the axle width. So if we say the radius for the left wheel is the center radius minus half the axle width, and we know that the left wheel radius is proportional to the its radius. So that's basically this formula up here, where I move the RL up there, so you get that. And then here you get the final formula for calculating the speed of the left wheel, and the speed of the right wheel will be very similar, except that it will have a plus here in the formula. And we can input this exact formula into our program. Now we have still one problem here with this formula, and it contains a factor r. So we have to know what the radius r is of the circle we're driving. And the radius is of course set by how much we turn the front wheel. So our next challenge is calculating the radius from the turn of the front wheels. For this I prepared this board. You can see that if I would lengthen the axles of the front wheels, at some point this line would cross the line of the axles of the back wheels, and the turn radius will be somewhere here. The problem is these wheels are in parallel and there is no clear center of radius. And to work around this, I will assume that there is an average front wheel drawn here, and and let's calculate the angles like this. So let's forget about the real front wheels, but let's assume it's a trike. It makes the calculation slightly easier, and from there we have a clear intersection from the extension of the front wheel driving axis actually with the rear wheel driving axis, and we have a clear start and end of the turning radius. So our challenge now is to calculate r from the numbers we have here. We know alpha because that will be the input for steering that we get from our gamepad or programmatically, and but we don't know delta or beta per se. We know that this is a 90-degree angle. So we know a few things. One thing that we know is that the tangents of this angle here equals L divided by R. We know L, we can measure that on the car, but we don't know delta, and R is the number we're looking for. We also know that alpha plus beta here in this triangle plus 90 is 180 degrees, because this here is a straight line. And from that we can know that delta must be equal to alpha, because delta is in a triangle here with the same beta, and we know that also the when we add up all the corners in one triangle or all their angles, it also sums up to a total of 180 degrees. So this means that delta must be equal to alpha, and that's very handy, because from this we can know that tangents alpha is L divided by R, or if we flip those two terms around, so we move the R up and tangents delta down, you can do that by first multiplying both sides with R and then dividing both sides with tangents delta or tangents alpha for this reason. This means that we have found R, and we can calculate R from the angle here with which our front wheel turns. So the math turns out really simple. Those two formulas here for the left speed and the right speed, and for calculating the R, are the basis for our program. Now let's program this into a Spike Prime program and see if that really works. Good. Now for our program, let's define some variables to represent the numbers from our formulas. For instance, the letter L, or let's make it a capital L here for easy legibility. And the L, so the distance between the front and the back wheels, is 120 millimeters in our case. Let's make another variable called h, and h is half the length of the rear wheel axle. In my case, in the case of the hot rod, it's 57 millimeters. And then we have another variable that we need called ratio, and ratio is the gearing ratio that we put onto our front wheel motor, because we geared it down, at least I wanted to gear it down a bit, because it allows me to drive more precisely. And first, at least on the output, there is a 20th gear, and on the motor there is a 12th gear, and so this let's set a ratio. So this ratio will help us convert the angle of the motor to the real angle of the wheels. Now, now that we've set these numbers, let's center our front wheels. So our front wheels are here on port F, and in my case, if I want them to be perfectly centered, I have to drive the front wheels to position 9, so it's just 9 degrees off. And then to save that position, I will here set the relative position there to 0, and then calculate every angle in the future from this relative position. Good. I think now we are set up, and I will create a my block with a text label. So drive at speed, and then speed, and another text label with front wheel angle, and let's make this angle and save my block. This allows me to drive at different speeds and different angles later. So for now, let's see what happens if we drive at speed 50 with an angle 15. Now, if we want to do this, so let's now fill out our my block. Of course, we have to drive first our steering wheel, so we drive to a relative position angle, because that's the angle where we want to go at 100% speed. But that doesn't really work, because it only drives the motor to that position, but not necessarily the wheels. So we have to multiply that by a ratio, by this gearing ratio, to get the wheels to the exact position. So where's my variables? Good. So this will bring the front wheel positions to that exact ratio. Next, we have to calculate the radius that results from this angle. So let's make another variable here and call it radius. Remember that the radius was the length of the car divided by the tangents of the turning angle. So let's go back here. That was the formula that we found. So the length of the car divided by the tangents of this angle, which is the same as that angle, which makes it really easy. So we can just input it like that into this software. So there is a division here. There is the length of the car called L that we input at the beginning, and then we have a formula, or at least a function. It's a tangent function and we can use angle for that. Now that we have the radius, we can calculate the speeds. Remember that the wheel speeds are the central speed times their respective radius divided by the full turning radius. Now we have found the full radius here, and we know from our my block what our target speeds are. So let's set our motors to these speeds, and so they will be let's make a division here, and ultimately we have to divide everything by the full radius. So remember here this, then we have to subtract two numbers, being the full radius minus half width. So we have both of them into the variables here, radius minus half, and we have to multiply that whole thing by our target speed, like this. Now we can duplicate all that, and then here instead of adding we need to instead of subtracting we need to add. Okay, and now our speeds are set, and let's start the motors now. Now oh, this is of course the B motor. Now since motor A is on the right side of the car, we can make it run forward. Since motor B is on the left side of the car, we can make it run backwards. After running them, we can stop both motors, and of course we don't stop them right away. We wait a bit. Our motor is starting in the right direction, and we will be running a speed with this angle for 1 second. Now let's see if that works. If you like this video and you like to see more of them, remember to subscribe. I'd really appreciate that. That obviously didn't work. I think I made a mistake between the left and the right wheel. Let's turn a bit more to make it even more obvious. So let's I increased, yeah, here you see it. So the front wheels want to turn left, but the back wheels want to turn right. Okay, I think I made a mistake here, because actually motor A is on the right side, so it should have the plus sign, and motor B is on the left side. So let's switch these two radii around. Now it's right, so motor B is my left motor, minus H, and motor A is my right motor, plus H, and see if that works better. That's much better. So that's a really smooth turn where the speeds of the back wheels are proportional to the angle of the front wheel, and it turns really smoothly. Let's see if that also works backwards, and then run the program again. Yes, it works. Now let's see what happens if we change some movements. My table is pretty small, so I'll bring this down to half a second. Then I'll duplicate this block here. So let's drive forward 50, turn 30 to the left. Let's make this negative 30 to the right. Then let's drive forward somewhat straight, and then let's drive backward with a very small angle, it this way and see if that works. Okay, let's run the program. Wow, that was kind of like we expected. So here is our basic program. You can build on this to run your own obstacle courses, or even connect a gamepad to this program and make your car run remote controlled with an electronic differential. And there you have it, a Spike Prime car that handles like a dream using its own electronic differential. Now it's up to you to build your own car. You can design your own using 2 motors and a steering mechanism like this, or you can head over to antonsmindstorms.com and download the building instructions for this car. I worked hard to make easy steps to include the wiring in the building instructions, and I even made a version with a single black wheel, so you can drive the car even without all the differential math. Hey, thanks for watching. Remember to like, share and subscribe for more awesome projects like this one. See you in the next video. Bye bye!